want to solve this week is as follows. Suppose we know that the product of these two quantities is equal to 1. Then we want to show that it must be true that x and y must add up to 0. First, let's note that this product does not have to equal 1. For example, suppose that x is 1 and y is 2, then this product becomes 1 plus the square root of 2 and 2 plus the square root of 5. And 1 plus the square root of 2 times 2 plus the square root of 5 is approximately 10.22, which is definitely not 1. On the other hand, if I make x equal to 1 and y equal to minus 1, then I get 1 plus the square root of 2 for this quantity, and putting in minus 1 for y, I get negative 1 plus the square root of 2. And when I multiply this through, I do get 1. Try it and see. And note that x plus y is indeed equal to 0, because 1 plus minus 1 is 0. And what we're being asked to prove is that this is not a coincidence, but that whenever this product is equal to 1, then x plus y will indeed be equal to 0. In this video, I'm going to show two methods for solving this problem. One method involves the manipulation of radicals and powers. The alternative method is more of an abstract algebra approach. For method 1, I first need to make two observations. Note 1. Let's recall the following algebraic property. It says that if you can prove that a product is not 0, then that means that neither factor can possibly be 0. So if a times b can be proved to equal to 1 or minus 1, then it follows that a is not 0 and b is not 0. Note 2. Let's recall the property of the difference of squares. The quantity a minus b times the sum a plus b is equal to a squared minus b squared. Whenever I see an expression like this with a radical in it, I think of the difference of squares, because I know that multiplying by the radical conjugate will help me eliminate the radical, and 9 times out of 10, that will help me solve my problem. So here, my a is x and my b is the square root of x squared plus 1. And so when I take a plus b and multiply by a minus b, I get a squared minus b squared. So I get x squared minus this quantity squared. But the square undoes the radical, so this becomes x squared minus the quantity x squared plus 1, which is just minus 1. And the radical is all gone. Let's observe, too, that by note 1, I have proved that this quantity cannot be equal to 0, because I have a product that's equal to minus 1, and so because 0 is not a factor of minus 1, it's not possible for this quantity to equal to 0. By the same token, it's not possible for this quantity to equal to 0 either. I can now use these two observations, note 1 and note 2, to solve the problem of the week as follows. So the problem says, given that this product is equal to 1, we're trying to prove that x plus y equals 0. So I'm writing down what I'm given. I'm given that this product is equal to 1. And the first thing I'm going to do is try to eliminate this radical expression by multiplying by the radical conjugate. But whatever I do to the numerator, I have to do to the denominator so that I don't change this equation. So if I multiply this quantity by 1, the resulting equation will be the same equation as what I started with. Now I know that this is equal to 1 because from note 2, I recall that I proved that this quantity, x minus the root of x squared plus 1, cannot be 0. And so when I take a non-zero number and divide it by itself, I do get 1. And also, by note 2, I know that this quantity times this quantity is equal to minus 1. And so this expression becomes here's my y plus the square root of y squared plus 1. And here's my denominator here. And then these two multiplied together to become minus 1. And so now this equation, which I started with, is equivalent to this equation here. What I can do next is I can multiply both sides by the reciprocal, like this, and I get that y plus the square root of y squared plus 1 is equal to the negative of this denominator, because I multiplied both sides by the denominator and then by negative 1. I'm now able to rearrange this expression a little bit as follows. So I'm rearranging this expression as follows. So what I did was I added x to both sides of this equation, and I subtracted the square root of y squared plus 1 from both sides. And I conclude that x plus y is equal to this difference, the square root of x squared plus 1 minus the square root of y squared plus 1. Now the problem asks me to prove that x plus y is 0. What to do? Well, I notice the symmetry in this problem. I notice that if I interchange the x and the y in this equation, I get exactly the same equation that I started with. And since this equation is equivalent to this equation, it means that if I interchange the role of the x and the y in this equation, it will still be true. Because when I interchange the x and the y in this equation, it's exactly the same equation. It's still true. And so that means, by symmetry, replacing x with y and y with x on the left-hand side, it becomes y plus x, which is the same as x plus y. And replacing x with y and y with x on the right-hand side, this expression becomes the square root of y squared plus 1 minus the square root of x squared plus 1. So what we've shown is that x plus y is equal to this quantity, let's call it b, but at the same time, x plus y is the negative of this quantity, or negative b. And so we have that x plus y is equal to b, but at the same time it's equal to negative b. And the only way for a number to equal the negative of itself is for that number to equal to 0. If you like, you could write it this way. We have that b equals minus b. Add b to both sides of this. It says that 2b is 0. Divide both sides of this by 2. so b is 0. And so the conclusion is that x plus y is b, which is 0. And this was the goal. So we've solved the problem. Namely, we've shown that if this product is equal to 1, then x plus y must equal 0. As an alternative, we can solve the problem of the week using a different method as follows. So my alternative solution looks like this. We're given that this product is equal to 1. We're trying to prove that x plus y equals 0. So I write down what I'm given, that this product equals to 1, and then I take the logarithm of both sides. And this is okay because if this equals 1, then the natural log of this is equal to the natural log of 1. And then I'm going to use the properties of logs like this. And so, for this step, we needed to recall the property of natural logarithms, which says that the log of the product is the sum of the logs. So here I have a log of a product, and I've written it down as the sum of the logs in this way. Now there's one concern with applying the natural logarithm to this product, because this property is true for positive a and b. Because if we take the log of a negative number, we're going to get a complex number. And I'm really assuming throughout this problem that I'm dealing with real numbers and not complex numbers. So I need to be sure that this quantity inside the natural logarithm is positive. And it is positive. Let me show you how I know. Note 3 is that this quantity, x plus the square root of x squared plus 1, is positive for every real value x. And how I show it, this is obvious if x is positive, nothing to show. I have a positive quantity plus a positive quantity, it has to be positive. But what happens if x is negative? Well, basically what's happening is that when I square x and add 1 and take the square root, I'm getting a quantity that's larger in magnitude than the magnitude of x, so that when I add it to x, even though x is negative, I'm still getting a positive quantity. And I can show that step by step like this. First observe that x squared, when I add 1 to it, is strictly greater than just x squared for any value of x. In particular, if x is negative, this is true. Then I take the square root of each side of this inequality, and when I do that, the inequality is maintained. And that's true because the square root function is an increasing function, so it preserves inequalities like this. So whenever b is larger than a, when I take the square root, you find that the square root of b is still larger than the square root of a. So in this inequality, my b is x squared plus 1, which is greater than my a, which is x squared. And so the square root of b is greater than the square root of a. For the next line in my proof here, I note that the square root of x squared is just another way of saying the absolute value of x. So this says that the square root of x squared plus 1 is greater than the absolute value of x. But we're assuming that x is negative, so the absolute value of x is found by taking the negative of x. And this strict inequality is true for all negative x values. So when I add x to both sides of this inequality, we have the square root of x squared plus 1 plus x is strictly greater than 0 for all x less than 0. So in either case, whether x is positive or negative, the quantity x plus the square root of x squared plus 1 is positive. Oh, and certainly if x is 0, this is obvious. If I put in x is 0, I have 0 plus 1, which is certainly greater than 0. Taken together, we have shown that in either case, if x is greater than or equal to 0, or if x is negative, the quantity is indeed positive. And so I should have no qualms about taking the natural logarithm of this positive quantity. Which I did in this step of the proof. So that's okay, because we proved that this quantity is positive no matter what the value of x. Now this is a common and useful trick to try. Whenever you see a product, take the log to turn it into a sum. Or whenever you see an exponent, take the log to get rid of the exponent. But what does this step accomplish, you might ask? Well, there's an interesting algebraic identity that says the natural log of this quantity is equal to the inverse hyperbolic sine of x. And if I replace this quantity with the inverse hyperbolic sine, that's going to make the rest of this proof very easy and will be solved in 2 or 3 lines. We're almost done. If you didn't know this algebraic identity, stick around, and after I'm finished with this alternative solution, I'll explain to you why this is true. So, applying this algebraic identity in the next step, so that was an identity, we now have that the inverse hyperbolic sine of x plus the inverse hyperbolic sine of y equals 0, and subtracting this quantity from both sides of this equation tells me that the inverse hyperbolic sine of x is equal to the negative of the inverse hyperbolic sine of y. Now, an interesting property of the inverse hyperbolic sine is that it is an odd function. And so I can pull the negative into the argument like this. I can show you a picture of what I mean. So this graph gives a picture of the hyperbolic sine of x, which you can recall is defined by this ratio involving the exponential function. And so it's a strictly increasing function, which means that it's 1-to-1 and invertible. And so the hyperbolic sine function has an inverse function, the inverse hyperbolic sine, which is this function, which is found by taking the red graph and reflecting it across the line z equals x in this graph. And because the hyperbolic sine function is an odd function, and because of this reflective property, it follows that the inverse hyperbolic sine function is also an odd function. So if you take the inverse hyperbolic sine of negative x, you get the negative of the inverse hyperbolic sine of x. Which is just the property that I used right here. I took the negative sign and pulled it into the argument right here. Because the inverse hyperbolic sine is an odd function, I can do that. The next property I'm using about the inverse hyperbolic sine is that it is a strictly increasing function, so it's 1 to 1. And that means that whenever you plug in two different arguments, if you get the same quantity, those arguments must be the same. And that's how come I know that x must equal minus y. And that's because the inverse hyperbolic sine is a 1 to 1 function. And we've solved the problem, because this proves that x plus y equals 0, which was the goal. So, summing up this alternative solution, what we did was we wrote down what we were given, which is that this product is equal to 1, and then we took the natural logarithm of both sides. Then we used the property of logarithms, which says the natural logarithm of the product is the sum of the natural logarithms. We made sure that this quantity here is indeed positive. Then we used an algebraic identity that replaced this natural logarithm quantity with this inverse hyperbolic sine quantity. We subtracted this quantity from both sides. Then we used the fact that the hyperbolic sine function is an odd function. And then, after that, we used the fact that the inverse hyperbolic sine function is a 1 to 1 function, so that when we take the hyperbolic sine of both sides here, we get that x is minus y, and hence our goal, x plus y is 0, and the problem is solved. If you're wondering where this identity came from in my proof, and how is the inverse hyperbolic sine related to the log function in this way, I can explain that as follows. So here's the proof to my claim that the inverse hyperbolic sine is related to the natural logarithm function in this way. Let me just give this guy a name. I'm going to call him x. So x is the inverse hyperbolic sine of y. That means, recall, that if I take the hyperbolic sine of both sides of this, I get the hyperbolic sine of x is y. But the hyperbolic sine of x is defined using the exponential function in this way. So y is the hyperbolic sine, which is e to the x minus e to the negative x over 2. Multiplying both sides here by 2, I get this expression. And now I'm going to multiply both sides of this expression by e to the x. And I recall the property of exponents to do this. So if I multiply both sides here by e to the x, this becomes 2y times e to the x. And here I get e to the x times e to the x, which, recall, is e to the 2x. So this became e to the 2x, minus, when I multiply this quantity by e to the x, I get 1. Because e to the minus x times e to the x is e to the 0, which is 1. And what has that done for me? This gives me a quadratic expression in e to the x. Because, let me call it w. If w is e to the x, then w squared, right, is e to the 2x. So, this is w squared minus 2y times w minus 1 equals 0. And this is a quadratic equation. And I can use the quadratic formula to solve for w. And once I've solved for w, I can take the natural logarithm to solve for x. So here comes the quadratic formula. which, recall, goes like this. And so if I match these equations, I have a is 1, b is minus 2y, and c is minus 1. And the quadratic formula says that the answer is this formula. So plugging ABC into this formula, b is minus 2y, so negative b becomes positive 2y, plus or minus the square root. We have b squared here, and b is minus 2y, so when I square it, I get 4y squared, minus 4ac, a is 1, and c is negative 1, and the denominator is 2a, and a is still 1. So solving for w in this expression, w equals this, and with a little bit of simplifying and a little bit of algebra, this simplifies down as follows. So this expression for w simplifies down as follows. We have 2y plus or minus the square root of 4y squared plus 4 over 2. I can factor the 4 out from the radical, and it becomes 2. My 2's cancel, so w, which is e to the x, is equal to y plus or minus the square root of y squared plus 1. Finally, recalling that e to the x is always positive, it never goes negative, that means that I must choose the positive solution to this equation. So it follows that e to the x is y plus the square root of y squared plus 1. But x, recall, is equal to the inverse hyperbolic sine of y. That was right up here at the very first step of my proof. It's scrolled off the screen now. And so that's what I wanted to prove. So I can solve for x here by taking the log of both sides, and I'm going to get it like this. So if e to the x is equal to this quantity, then the log of e to the x is equal to the log of this quantity, but the log undoes the exponent, and the log of e to the x is just x. So x is the natural logarithm of this quantity, but at the very top line of this proof, remember, we identified the inverse hyperbolic sine of y as x, and so we've proved the algebraic identity that the inverse hyperbolic sine of y is indeed equal to the natural logarithm of this sum. It is interesting to compare the two solution methods shown here for solving the problem of the week. We see that the first method uses algebraic manipulations of powers and radicals, and also a symmetry argument. The alternative solution is a slightly more abstract algebra approach. It uses the property of logarithms, an algebraic identity, and properties of odd functions and one-to-one functions. There are no manipulations of powers or radicals at all, and no symmetry argument. Neat! This comparison also provides a window into the interconnection of the concepts of powers and radicals on the one hand, and the concepts of exponential and logarithmic functions on the other. It provides a hint that the concepts of sines and cosines are inextricably linked to the exponential and logarithmic functions. These are concepts from the field of complex analysis, which turn out to be powerful tools indeed, which many mathematicians and scientists need to have in their problem-solving toolkit.